All right, we're moving into the real stuff now. I feel like this is where pre-calculus really becomes pre-calculus. Because we're going to talk about exponential functions now, and then we talk about logs, and then we do trig. And so we're really starting to do like the things that are very classic to pre-calc. In my opinion, things before this are useful and nice, but the remaining material is really kind of the most important stuff, right? It's potentially the most challenging, it's potentially the most new, and it's potentially the most useful. So just be aware of that, and keep up the good work here as we keep going. So an exponential function, just kind of looking ahead here, these are what they look like, right? And we've got a whole bunch of them being graphed here, that's why they look a little bit strange. But let's read the top box first. So the exponential function with base a is defined for all real numbers x, and it's given by this general form. And so you can see a is some positive number that's not equal to 1, and x is a variable, right? So this is the general form of an exponential function. The a is some number, not 1, and the x is a variable. So let's point out a few things about this definition. What does it mean that it's defined for all real numbers? What's that telling us? What's another vocab word that we've learned that's telling us about? It's defined for all real numbers. It's telling us we can plug any number into this function. What does that mean? I'm sorry? Not rational, but what does it mean when we can plug numbers in? When do we talk about plugging numbers into a function and what you can and can't plug in? There's a specific word for that. I'm sorry?
Is it a negative number?
It's not a negative number. I'm thinking of a vocab word that we've been doing in most sections. Starts with a D. I'm not going to let this one go. Stephen? Domain, yeah. This is telling us that the domain is any number. It's saying it's defined for all real numbers. That means that the domain is any number. And so keep that in mind. That means you can plug anything into these, right? You're never going to divide by 0. You'll never take the root of a negative. There's no issues in exponential functions. That's kind of important. We always assume a is some positive number, and we don't want it to be 1, because if a is 1 in this function, we'll have 1 raised to the x, and 1 raised to any power stays 1, right? And so if a is 1, then our function just ends up being the number 1. And that's just a straight line, and so it's boring, and so that's why we just assume that it's not 1. We want to get curved functions like this. We don't want a straight line. Oops, sorry, that was peeking off the page a little bit. So if a is 1, we end up with the function 1, which is just a straight line. And we want to use curved functions. And we want to use curved functions because we use these things to model things that have curved characteristics. So I'm sure you've heard the word, oh, that thing increases exponentially, right? That's because when something increases exponentially, it keeps increasing faster and faster and faster. And see how these graphs are increasing in a faster and faster way? And so anytime something increases exponentially, we can use an exponential equation to graph it, to model it, I should say. All right, I'm getting a little ahead of myself, though. The other thing we want to take away from this top piece is the word base. So base A just means whatever the number is that's being raised to the power x. So in these couple examples here, we've got 3 quick examples. This one has base 2 because it's 2 to the x. This one has base 3 because it's 3 to the x. And this one's base 10 because it's 10 to the x. Okay. I've already kind of pointed out what they look like a little bit, but let's make it a little more clear. So there's a whole bunch of ones being graphed here, and if yours is in black and white, it's a little hard to look at. It's a little bit nicer that's in color here. But you can see that there's a couple things we want to point out. First of all, notice that all of them have the same y-intercept. Even though they're kind of doing different things, all of them have a y-intercept of 1. Even if they're increasing really fast or they're decreasing, it doesn't matter. They all cross at y equals 1. What What other characteristics you notice? I mean, I can point them out, but like, what else is going on here? We're graphing 1, 2, 3, 4, 5, 6, 7, 8 functions here. And what do you see about them? Like, what are the ones that are on the right side compared to the left side? What's the base, the difference between bases on those two? Manuel?
The ones on the right side are full powers and full numbers, and the ones on the left side are fractions.
Yeah, these ones on the right are all whole positive numbers, and these ones on the left are all numbers that are between 0 and 1. And so that's one thing I want to point out. I'm going to write down some characteristics. The first thing is that if the base is positive, so if A is bigger, if A is bigger than 1, not positive, they're always positive. If A is bigger than 1, then we have an increasing function. And by increasing, I mean when you go left to right, these things go up. Right? When I'm looking at all these ones, they start over here, and they increase, and they go up. And so if we have a base that's bigger than 1, the function increases. And say something more about that. Notice how 2 is the one that's the farthest to the right, and then 3 is here, and then 5 is here, and then 10 is here. Right? So what do you notice? That as the base increases, the function gets steeper. Right? See how 2, 3, 5, 10? So not only is A bigger than 1 mean it's increasing, but the larger the base, the larger the A or the base, the faster it increases. And that should make sense, right? If you raise a number, like if you raise 2 to a power, that's going to be less than if you raise 10 to a power. Right? And that's literally what's showing us in this graph right here. 2 to the x is less than 10 to the x, right? If the number is between 0 and 1, like all these, it decreases, right? So if A is between 0 and 1, then the function decreases. And the characteristic that we can see here is that notice how 1/10 is kind of the steepest decreasing one, 1/5 is the second steepest, 1/3 is the third steepest, and 1/2 is the least steep, right? And so the closer these numbers get to 1, sort of the less steep they are, or the flatter they are. I think of them as being flat. And so that's what I want to say. The closer to 1 that A is, the flatter the graph is. Or less steep, you could say. And so we've got kind of those characteristics about this thing. That's why there's a whole bunch of them being graphs. You can see those things happening. You can see that they all cross at y equals 1. You can see that if the base is bigger than 1, they're increasing. The bigger the base, the steeper the increase. Alright, so now we've got some introduction to those things. We can talk about how we can graph them. We can talk about how we can use them. We can do all kinds of stuff with this. Are there any questions or comments right now? So this is kind of just summing up, not really summing up, it's sort of pictorially representing what we just said. So a lot of the stuff that we just said right here is being shown down here. And so it's telling us, first of all, something we already said, the domain are all real numbers and the range is 0 to infinity, right? See how it starts at 0 and goes to infinity? Another important thing is that the line y equals 0 is a horizontal asymptote, right? That's why we talked about horizontal asymptotes right before this. And so it's not being shown here. I'm going to draw it in. But there's horizontal asymptote of y equals 0 down here. See how the function's getting really close to that line, but it's never going to touch it? It just kind of goes out in this direction and never really touches that line. And same thing over on this one. And so we can see So notice, just to be real clear about this is important, exponentials have a horizontal asymptote at y equals 0. And we're now familiar with what that means. And the one on the left here is showing us an increasing function, and so this must mean that a is bigger than 1, just like we just said. And the one on the right is a decreasing function, and so that must mean a is between 0 and 1, again, like we just said. But really the main thing, aside from the bigger than 1 and between 0 and 1 thing on this, that I'm really trying to point out is that there's a horizontal asymptote at y equals 0. That's an important part here. So especially when we start to graph it. When we start to graph it, we need to know where that horizontal asymptote is. That's why I really want to point that out. Alright, so here's kind of the more straightforward problems we might have. If this is our function, f of x equals 3 to the x, let's find f of 2 and f of 3 halves, right? So this notation, f of 2, just means plug a 2 into the x, right? And so this becomes 3 squared, which is 9. So if our function is 3 to the x, then f of 2 is 9. How do we think about f of 3 halves? That's an interesting one. So obviously we plug 3 halves into the function. How can we sort of go further with that one? How can we simplify that one a little bit? What does a 3 halves exponent mean, I guess is my question. What does that mean, Disa?
It's the cubed root of 3 squared.
The other way around.
Oh, okay.
So
It's the square root of 3 cubed.
yeah, it's a square root because we put the 2 down here of 3 cubed. 3 goes there. Remember, we can write exponents as radicals and radicals as exponents, right? So we think about that as a radical. And we can't do too much with it. We can just write this as a square root of 27 if we want, and that would be as far as we can go, right? Square root of 27 is not a perfect square, so that's as far as we can go. Okay, that's good. Let's look at something else we can do with these things. And I haven't put in, or I should say there will be an application problem sort of later. I'm still working on that, but we'll do an application of this stuff as well. Let's look at the next page though. Is everyone all set with that one? Oops. So another type of problem we might see is that if we know we have an exponential function, and we know one of the points on the graph, then we can figure out what the base is. And so that's what this says. If we know that our function is the form y equals a to the x, right? So we know we have an exponential function, and we know a single point the function passes through, we can figure out what a is. You just plug in the point and use it. Suppose y equals a to the x for some base a, and we know the function goes through the point 4, 16. Find a. So when it tells us 4, 16, that's telling us an x and a y value, right? And it's telling us an x and a y value, and we have a y and an x in our function. So we can take this point and plug it into this general form and figure out what a is. So we can say 16 equals a to the 4th. And then we could solve for a. Right? How do we solve for a in that one? What do we do to get a by itself? How do we get rid of the 4th power? Not a square root, but a 4th root. Yeah, we want to get rid of the 4th power, and so we want to do a 4th root. And so we get, does anyone know what the 4th root of 16 is? 2, yeah, good. And what happens when we do a 4th root of something? We get a plus or minus. I think I heard that, right? So this should be plus or minus on the left, and then just a on the right. If we want to know what a is, though, we want to know whether it should be plus or minus 2, not both of them. And something on the last page is telling us which one it should be. Any thoughts about that? There's some condition on A. A has some condition on it that we must satisfy. What is it, Manuel?
It can be less
Yeah. Good. Remember on this last page we said A has got to be some positive number. We always think about the base as being positive. And so we know that A has to be positive, so from the previous page, A has to be positive, and so we choose the positive one. So A equals positive 2, and our function is y equals 2 to the x. Alright, so if we know one point it goes through, we can figure out what the base is. That's one way to do these kind of problems, or one type of problem you might see. Let's do this next one. So if this next one is very similar, we're saying we know we have some exponential function, find out what the base is. And so we're looking at this picture, and before we do anything, before we do any problem, I know something about what A is. Looking at the picture here and looking at the last page, what do I know about A? It's going to be a fraction. How do you know that? Yeah, because a function's going down, and I know that functions that have fractional bases go down. And so this one's going down, so I already know before I do anything it's got to be some fraction. That's very helpful to know that, right? And so just keep that in the back of your mind. A is going to be a fraction. Right? Let's make sure that happens. And so when I look at this, I see that we know y equals a to the x, and that it goes through the point minus 3 comma 8. And so that's telling us an x and a y, so we plug that into the function. So we say 8 equals a to the minus 3. And we think about that, right? This is kind of a slightly trickier one to solve, but we know how to solve these from the fraction section. We want to think of this as 8 equals 1 over a cubed. And we want to solve for a, right? And so we multiply both sides by a cubed so that they cancel on the left, or on the right, I mean. And we get 8a cubed equals 1. And then we divide by 8, and we get a cubed equals 1/8. And then we take a cube root. Right? We want to get rid of the cube, and so we do a cube root. And so we say the cube root of a cubed equals the cube root of 1/8. This is reaching back into the very first section, right, where we talked about negative exponents. Negative exponents become fractions. We're now solving a problem that has a fraction in it. And we're doing a radical of a fraction too. This is all stuff from that very first couple sections, first two sections, I guess. How do we do the cube root of 1/8? What is that property there? When you have a fraction inside a root, what do you do? Not 1/3, but you're on the right track, I think. What's the process? Yeah, you can break up the cube root into the top and the bottom. Remember, that was a property from the radical section. And I think that's what you were saying, Manuel. Yeah. But the difference is, when you take the cube root of 1, you get 1, and the cube root of 8 is 2. And so we get 1 over 2 for that. And so our a is 1/2, and our function is 1/2 to the x. And that fit with our, remember when we started this problem, we said, okay, a's got to be a fraction because it's decreasing. And we found out that it was a fraction. It turned out to be 1/2, That fits with what we were thinking, so that makes us feel good that we did it right. That's what it looks like. Questions? All right. So there's a very special kind of exponential, which is what's being shown in the bottom part of this page. This one's called the natural exponential function. Or sometimes people just call it the exponential. See that? It's often referred to as the exponential function. And it looks like this. It's e to the x. And so e is a number. It's like pi. Right? Sometimes we write pi, right? And you know that that means 3.14159, blah, blah, blah. So e is a similar kind of number. E is a number where it's right, I wrote it right here, right? E is approximately 2.718281828845, blah, 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 blah. And so it's also irrational. It's irrational, which means that, see this dot, dot, dot here? This means it just keeps going on forever. It never repeats itself. It's very similar to pi in that respect. It's a lot like pi, except it's a different number. And let's look at a couple. And so since it's about 2.71, the graph of it, you can see, is in between 2 to the x and 3 to the x. And that should make sense because e is less than 3 but bigger than 2. And so since it's between those two numbers, you can see that the graph ends up being between those two graphs. Right? And it's obviously closer to 3 than it is to 2 because e is closer to 3 than it is to 2. Right? So when you see e, it's not a variable. It's a number, just like pi. Since it's bigger than 1, it increases, right? That's what's being shown on the left here. So y equals e to the x is an increasing function because 2 is bigger than 1, right? This is like 2.72 to the x, approximately. I shouldn't write equal, I should write approximately equal to that. And so it's an increasing function. And this is e to the minus x. It's kind of hard to see the minus sign on the screen. You might want to look at your own paper, but this is e to the minus x, right? And so you could think about that in two ways. It's a horizontal flip, right, because you're doing f of minus x. This is a good review for the quiz today. It's a horizontal flip because you're plugging in a minus x. It's like we took the original one and we flipped it around like this. Right, it would look like that other one. The other way to think about that is it's like 2.72 to the minus x, which is the same thing as 1 over 2.72 to the x, which is the same thing as, well, yeah, that's what I wanted to write. That's it. Let me make it a little more legible for you. And so it's 1 over 2.72 to the x, and so it's decreasing. The other way to see that as decreasing is because it's a number that's less than 1. It's a fraction. And so that's why the other reason that one would be decreasing. Okay, so the exponential function, the exponential, e to the x, is really the one that you see most of the time. When you take your science courses and you talk about like bacteria growing in a petri dish or something like that, you always model it using the natural exponential function. It's called the natural exponential because it models phenomena that occur naturally a lot. And we'll see an application of that probably on Friday. Questions about this page at all? Before we graph it? So we'll graph some today. We'll do a little bit of graphing. We'll finish up with the quiz, and then we'll probably do the application on Friday. Can I answer any questions at this point, though? All set with this page. All right. This will be a good review maybe for the quiz today. We'll see how far we get. I don't know. So graphing these things using transformations. I skipped the page. Skip the page using a table. Graphing exponential functions. So we can use the above information, like the stuff on the previous pages, so that before we even graph one of these things, we already kind of have a good idea what it looks like. For example, you know, if the if the base is bigger than 1, we know it's going to be increasing. If it's less than 1, we know it's going to be decreasing, right? So we already kind of have an idea of how to do these things and what it's going to look like, and then we just want to fine-tune the graph a little bit and make it look a little bit better. And so we'll do it two ways. We'll use a table. That's what we're going to do on this page. And I'm probably only going to do one of these examples because it's beneath you, quite frankly. And then we'll use transformations. That's what I really want to focus on. That's going to be on the next page. Let's just do one table example. I don't know why I still use tables. Tables are so, I don't know, middle school or something. But anyway, the first thing, A, that's this page, right? Using a table. If we use a table, again, we already know the general shape before we start. If A is bigger than 1, it's going to be increasing. And if the base is between 0 and 1, we know it's going to be decreasing. And then we just create a table to fine-tune that concept. And when we make a table, we want to make sure we include x equals 0, because that's going to find the y-intercept. And then we just choose enough values so that we understand how the function behaves in both directions. And then we just plot those points. And so I'm just going to do one of them, I think. So let's do this one here. 2 to the minus x. So we could think of 2 to the minus x as 1 over 2 to the x, right? Because it's got a negative exponent, which is the same thing as 1/2 to the x. And so when you rewrite it like this, it's easy to see that it's going to be a decreasing function, right? So RA is less than 1. And so we already know that we're going to draw a decreasing function. Right, we already know before we do anything it's going to look something like this. And so let's just fine-tune it a little bit and get a couple nicer points on there. And we'll plot them. So we make a quick table. I choose some x values and I'm going to plug it into my function. Right, we want to make sure that we're choosing 0, because 0 is going to tell us the intercept, the y-intercept. And let's choose a couple positive points, like 1 and 5, and a couple negative points, like -1 and -5. And when I plug these values into this x, right, I did this ahead of time, and I got the following. When you plug a 0 in there, you get 1, right? You get 1/2 to the 0, which is 1. When you plug a 1 in there, you get 1/2. When you plug 5, you get 1 over 32. When you plug a -1 in, you get 2. And when you plug a -5 in, you get positive 32. And then we can just plot these things, right? So like I plotted values at 1 and 5, -1 and -5. I know that at 0 it's going to cross at 1. And you just start plotting these points, right? So at 0 we were at 1. At 1 we were at 1/2, so that's right here maybe. At 5 we were at a really small number, right? 1 over 32 is really small. So I'm just going to put this dot really close to the x-axis. And then at -1 we were up here at 2. And then at -5 we were at 32, so that's like way up somewhere. I'm going to put it way up here, although I don't know if that's quite accurate or not. But you can see we get the right shape when we connect these dots. We get this decreasing kind of function. And it fit the general idea of what we thought it should look like. And that looks pretty good. And so I don't like doing the tables anymore. I try to avoid graphing with tables because we don't need to do that. It's just such like a rudimentary, I don't know, it's just so basic that like you already know how to plug numbers into a function. I don't think it's worth spending time on doing it. What I want to spend time on doing, does that even make sense? What I want to spend time doing is talking about the transformations, because that's a more useful, It's more advanced. It's like a better technique. And so the questions about this, Will, before I sort of start transitioning into the transformations part? So instead of like graphing a bunch of points, which again I think is beneath you, quite frankly, let's think about this as a transformation. It's like we started with 2 to the x, and 2 to the x is something we know what it looks like. We know that 2 to the x has an increasing shape and that it crosses at 1, right? Compared to 2 to the x, what kind of transformation is 2 to the minus x? How do we go from 2 to the x to 2 to the minus x in transformation terms? What kind of flip?
Horizontal.
Yeah, it's a horizontal flip, right? This is like a g of minus x situation. If g of x was 2 to the x, then g of minus x would be 2 to the minus x, right? And so this is a horizontal flip. It's a horizontal flip of 2 to the x. And so that's really how we want to think about this. We want to think about starting with 2 to the x and then just flipping it horizontally, right? And then it would look like what we drew in the last one anyway. It would end up looking like this. It would have the same y-intercept, which we found anyway. It would just have a different shape to it, right? It would be going the other way. And so that's really how I want to think about these things, is using transformations. And so let's do a couple examples. This will be good review for the quiz today, because I'm going to ask you to do some transformations on the quiz. Yeah, sure.
So what would it look like if there's no deficit for a vertical reflection?
If it was a vertical flip, there is one on the next page, but we might not get to it. But it would look like, instead of going down like that,
No, like clearly.
oh, there'd be a minus sign out in front of the 2.
Okay.
Yeah, so a vertical flip. So a horizontal flip is when you multiply the x by minus 1. If it was a vertical flip, we'd multiply the 2 by minus 1. And we'll see one of those on the next. Let me just put the one up on the next page that I'm talking about. This one has a vertical flip in it because it's got the minus out in front of the base. Yeah, that's a good question. So I'm not going to do the other plotting points one. Let's spend some time looking at this instead. Transformations. So if we want to use transformations, so this is B. This is method B from the previous page. So again, we already kind of know the general shape before you start. You look at figures 1 and 2 to figure out whether it's going to be increasing or decreasing, right? Make sure you plug in x equals 0 just to make sure you find the y-intercept. And then you shift the graph using things from the transformation section like that's on the quiz today. And something that you should add to the top of your paper. I'm going to add it here too. Note, very important note. These things have a horizontal asymptote. And so if we shift up or down, then the horizontal asymptote moves with it. So let's write that. When you shift exponentials up or down, the y equals 0 asymptote moves with it. So just kind of looking ahead for a second, this second example here with the +1, this is a vertical shift because we added 1 outside the function. We're going to end up moving the asymptote with this one. I think we might have time to do, probably have time to do 2 here, so that's good. All right, so let's do this first one. So this first one's very similar to the last one. It's kind of like we started out with 10 to the x, and we plugged in a minus x, just like in that last one. And so this is another horizontal flip, right? So this is a horizontal flip of 10 to the x. Does that make sense? And so, you probably won't need to do this very often, but I'm just going to show you this in case you need to, right? 10 to the x is this one. This is what 10 to the x is. It's a very steep increasing exponential. And so we're going to take that and flip it horizontally, and it's going to become this one here, the 1 over 10 to the x. It's going to become this decreasing one, right? It's like we're flipping it horizontally. And so that's what we're thinking about doing. So it's kind of like we start with 10 to the x, which looks like this. That's what 10 to the x looks like. And we're going to flip it horizontally. And so it becomes a decreasing function going through the same point. And since we didn't move, we just flipped it, right? We just flipped it, so the intercept should stay the same. But just in case we weren't sure about that, we can always just double check, right? We can always double check the y-intercept by just plugging in x equals 0. So you get y equals 10 to the 0, which is 1. And so it turns out it does stay at 1, right? And I also just want to add in there the asymptote. Right? There's an asymptote down here at y equals 0. And I want to point that out because that really comes into play in this next one where we move things up. Question about this one before we look at that next one? So this one wasn't too bad, right? It was just a flip. It didn't change the intercept. It didn't move the asymptote. So this is about as straightforward and basic as a problem can get. This next one's a little more complicated because we've got a -4 in the exponent and a +1 outside. And so first of all, I just want to note that we're transforming the function f of x equals 2 to the x. What's the x minus 4 doing? So instead of 2 to the x, we have an x minus 4. And so it's kind of like we plugged in an x minus 4 into 2 to the x, right? What kind of transformation is that? This is very relevant for today's quiz. It's a horizontal what? It's a shift, because we're subtracting 4, right? We're doing f of x minus 4, so it's a horizontal shift which way? To the right, yeah. So this is going to shift 2 to the x to the right 4. And then the +1 is like we're adding a 1 to the outside of it. Right, it's like we have a 2 to the x plus 1. And so what's that doing? Yeah, it's moving it up 1. So it moves 2 to the x up 1. And what I really want to point out, I almost don't have room to write it in here, but I'm going to do it anyway. Really important. The y equals asymptote, y equals 0 asymptote moves up with it. Since we moved it up 1, that's what this note's about. When you shift an exponential up or down, you've got to move the asymptote with it. So I'm just going to do that before I do anything else. I'm just going to draw in my new asymptote at y equals 1. So whatever I draw, it's going to get close to that asymptote as we go. Questions so far? Before we go ahead and draw that? Does everyone see those two different transformations? On the quiz today, I'm going to ask you to do things just like this. It's not going to be an exponential, obviously, but it's going to be similar kinds of moving up, down, left, right, flipping type things. So that we've seen a horizontal one, we've seen a vertical shift, and a horizontal shift as well. So are there questions about any of those shifts? Yeah. Like why is this one here? It's because when we add this 1 to the function, it's just moving the entire graph up, including wherever the asymptote is. So on the original graphs, let me show the picture of the original one. On that first page. On these ones here, these get really, really close to 0 down here and really, really close to 0 down here. But there's nothing being added to that on the outside. So when we add a 1, it makes it so that the lowest point is 1 higher. And so since the lowest point used to be really close to 0, on this one it'll now be close to 1. And so it just shifts all the points, including the lowest point. Alright, let's finish this one up quick here. So 2 to the x looks like this. And so 2 to the x, I'm just going to draw that in first. 2 to the x normally looks like this. 2 to the x. And now we're going to move that up 1 and left 4. And so it's going to get close to this new asymptote, but it's going to be a little bit higher. And so this would be 2 to the x minus 4 plus 1. And let's figure out that y-intercept. You set x equal to 0, and you get y equals 2 to the 0 minus 4 plus 1. And so this is going to be 1 over 16 plus 1, which is 17 over 16. And so this new intercept is a fraction 17 over 16. Let's take a look at the next one here. This next one's a little bit straightforward. I wanted to kind of just do a straightforward e to the x example. And so if you remember, e to the x is about 2.72, right? So you're thinking about e as about 2.72 raised to the x. And what we're doing here is we're taking that function e to the x and we're adding 1 to it, right? And so this is just shifting e to the x up 1 in this problem. But an important thing that we mentioned last time, which I will just flash up here real quick, is that these things have an asymptote, and so when we move them up or down, we got to move the asymptote with it. Oh, it's actually at the top of this page, I forgot. Right, note, when you shift exponentials up or down, you move the asymptote with it. And so when we move this one up 1, we want to make sure that we move the horizontal asymptote with it. So move the horizontal asymptote with it. And so it's usually at 0, 0, and so it's going to move up, it's usually at y equals 0, and so it's going to move up to y equals 1. So we've got that asymptote, and it's going to look the exact same as regular e to the x, just moved up 1. And so it'll look like this. And if we want to know the y-intercept, we don't really have to do any calculations, right? It used to be at 1, and now it moved up 1, so it's going to be at 2. But just to be clear about that, if you're ever unsure, just plug in a 0. Plug in x equals 0, right? We get 1 plus e to the 0, which is 1 plus 1, which is 2. And so you can always just double check that if you're not certain about it. So that was a nice warm-up one. That was pretty straightforward. Is that okay? Are there any questions about that? So the next one's more complicated, right? There's a lot going on in this one. We've got a minus sign out front. We've got an x minus 1 in the exponent, and then we've got a minus 2 in front. And so let's dissect this one piece at a time. So the first piece, let's talk about the minus 1. The minus 1 out front is flipping e to the x, because we're multiplying by minus 1. And so this is flipping e to the x vertically. The minus 1 in the exponent, this is plugging in an x minus 1 into the exponent. And so this is going to shift e to the x to the right 1. And then the last piece, the minus 2, is subtracting 2 off the function, right? We're taking the function and subtracting 2. And so this shifts e to the x down 2. And just like the last one, when we move the function up or down, we have to move the asymptote. So, and it moves the asymptote with it. So we're starting out with e to the x. So I'm just going to draw the base function on this one. That's what normal e to the x looks like. And so we're flipping it upside down, so it's going to be going downwards, right? It's going to be going like a downwards shaping thing. We're moving it to the right 1 and down 2. So I'll draw in the asymptote right away. I know there's this asymptote here at -2. And then we're flipping it over upside down and moving it to the right. And so it might end up looking something like this. So this is what minus e to the x minus 1 minus 2 might look like. Whoops. Yeah.
I'm pretty sure you answered this last class, but I can't remember. Like, how do you actually know it's shifting to the right?
Yeah, so the horizontal shifts on these things are really hard to show because it just looks very similar all the way. And so the way that we show the horizontal shift is really with this y-intercept. So, if it didn't have a shift, this y-intercept would be down at minus 2. Minus 2? It would be a -3, I'm sorry. Because it used to be at 1. And so if we just flipped it upside down and then moved it down 2, it would be at 3. But moving it to the right is making it so that it's not at 3 anymore. So let's show what the y-intercept is, and that'll kind of prove we moved it. So we plug in a 0, and we get e minus e to the -1 minus 2. Right? So this is about, if we want to write out what that is, it's like minus 1 over 2.72 minus 2. And so when you plug that into a calculator, that's about 2.3, minus 2.3. And so instead of being at -3, it's at minus 2.3, and that's really how we're showing that it shifted. Like visually, there's not too much of a difference, and since we're just sketching these things, we're not really being super careful, it's hard to show the horizontal shifts. And so the intercept becomes particularly important because of that. Questions about that? And there's no x-intercept, right? There's no x-intercept because it's never going to get above this line. This asymptote's pinning it down below that line, and so there's only a 1 y-intercept. All right. So I promised I would give a little application example today. I am doing that. You'll see one of these in homework. One similar to this one at least. Any questions about this graphing stuff? We're going to graph another one on this page, as you can see. But are there any questions from that last stuff? Okay. So I mentioned this last time, but the way that this comes up a lot, and I think the reason that this is often in pre-calc classes, exponential applications that is because they get used a lot in science classes when you're measuring the population of something, especially something that increases a lot. So I had mentioned last time, like growing bacteria in a petri dish is often modeled using exponentials because it increases really quick. But if something just increases at a fairly consistent rate or consistent pace, you can often fit an exponential model to those populations. And so I kind of made some up, but these are real types of models that you might see in research papers. And so I've made these 3 towns up. Obviously, I've taken local town names and played some words on them, right? So we got Pfister, Wartburg, and Beantown. And each of them can be modeled by an exponential function. And by each of them, I mean the population of them. And so we might be interested in knowing what populations are increasing and decreasing. How do we know that based on this information? From something we learned last time. What is it about the function that tells us whether or not it's going up or down? Can I remember that? Remember that?
If A is smaller than 1,
Then what?
then it decreases.
Yeah. So we had, trying to find that picture from last time. Here it is. We had this picture last time that said if the function has a base bigger than 1, it goes up. And the function has a base that's a fraction between 0 and 1, it goes down. And so an increasing population would look like the left-hand one, right? That's a thing that's going up. And a decreasing population would look like the left one. And so when we look at these 3 problems, I mean, we kind of look at the A's and think about which ones are bigger than 1. And so I'm just going to note this by their first letters, F, W, and B. And so Pfister and Wartburg have A bigger than 1, right? This one's got an A of 1.14, and this one's got an A of 0.65. I'm sorry, not Wartburg. Got ahead of myself. Beantown. So F and B have A bigger than 1. My goodness. A. And this one's also the A. And so since those have an A bigger than 1, they are increasing. And then Beantown has an A that's between 0 and 1. My goodness, Wartburg, thank you. Has an A that's between 0 and 1. And so it's decreasing. Which one's increasing the most? The quickest? The fastest? Yeah, Beantown's got the biggest A, right? 1.6. And so that one's going up the quickest. Just to be clear about that. The way I set this up is I said that these populations are the populations of these towns T years after 2000. So if we want to know what the population in Beantown in 2000 is, 2000 is T equals 0 because it's 0 years after 2000, right? 2000 is 0 years after 2000. Question? I used to get confused by that statement. I don't know if anyone else is, but T years after 2000. So if we're in 2000, we're 0 years after 2000, right? So we plug in a T equals 0 if we want to know what the population in Beantown was. And so that would be P equals 29,000 times 1.6 to the 0, which is just 29,000. And if we want to know the population in 2005, that would be T equals 5, right? Because that would be 5 years after 2000. And so 2005 is T equals 5. And so we'd get P equals 29,000 times 1.6 to the 5. And it turns out that's a pretty big number. I won't bother sort of plugging into a calculator, but it's in the hundreds of thousands. And so that's a really, really fast population growth. Maybe not realistic, but that's what you get when you make up a problem. Yeah, so let's graph these things then. So we're going to graph the Pfister and Wartburg populations. And we already said that one of them's increasing and one of them's decreasing, right? And so one of them's going to be going upwards, and the other is going to be going down. So let's do the Pfister first. So Pfister has a population P equals 900 times 1.14 to the T. So this is a transformation of 1.14 to the T. Right? We're taking 1.14 to the T and multiplying it by 900. But we're not shifting it up or down, so it still has an asymptote at 0. So I'll go ahead and draw in the asymptote right away. That's the y equals 0 asymptote. It's not moving. And so if 1.14 to the t might look like this, say, maybe it does something like that. So what is 900 times that going to do? What's the transformation doing? It's kind of like one of the ones that was on the quiz. What do you? It's not. Yeah, it's a stretch. Maybe that's what you meant, but it's not moving up or down. It's a stretch because we're multiplying the function by 900. Does that make sense? Is that what you meant? So yeah, that's what we're doing here. This is a vertical stretch of 900, and so it's going to increase a lot faster than that one. I will just sketch it here, but it's not going to be the best sketch because it's going to be such a different scale, but it's just like a much, much steeper line. Much, much steeper. Much steeper than that even.
If you stretch a graph enough, does it kind of, like, does it become more like of a straight flat line?
Yeah, it becomes more and more vertical looking.
Okay.
Yeah, so this one even probably looks more vertical than I drew it. It's going to be super, super vertical. Because think about it, 5 years later on this one, we plugged a number in the other one. But if we plugged a 5 into this one, it would also be a pretty big number. And so that's just showing us we have like a huge, steep increase on that graph. Other questions? And so the other one's similar, right? When we do 1,000 times 0.65 to the t. We're doing the same kind of thing, except we're stretching out a decreasing function. So it still has our asymptote at y equals 0. We're stretching out 0.65 to the t. And so 0.65 to the t, let's say that looked something like this. This is our old function. That might be 0.65 to the t. And so what we're doing is we're taking that same exact function and multiplying it by 1,000. And so that's going to be, again, a vertical stretch. And so I'm going to make this one look much more steep. I'm going to try to, at least. Let's see how I do. And then down here, it's actually going to end up below that line. Is that true? Yeah, eventually it'll go below that line, yeah. And so the red one then is our transformation. Questions about that? So you'll see a couple like this in the homework. There's a homework called Exponential Applications. And in that homework you see some functions that look a lot like these three things. And it asks you about like which ones are increasing, which one's decreasing, which one's increasing the most, etc., etc. It's very similar kind of questions to this.